Today we're going to talk about the first part of section 9.2, limits at infinity. So for example, what if we wanted to look at the limit as x is approaching infinity of 1 over x? What does it mean for x to approach infinity? That means x is increasing positive without bound. In other words, it's getting bigger and bigger and bigger in the positive direction. Well, infinity isn't a real number, so we can't actually plug infinity in. So when we're taking the limit, we're trying to see what happens to this 1 over x function as x gets really, really, really big in the positive direction. So we'll just pick x values that are really big, like 10, 100, 1000, and we'll plug them into 1 over x and see what happens. When we plug in 1, we get 0.1. Plug in 10, we get 0.01. We can plug in 100, 1000, 10,000, 100,000, a million, and 10 million, and what do you notice the function is doing? The function is getting smaller and smaller and smaller and smaller. Well, if you think about it this way, if you take one cookie and you divide it by a million people, how much cookie is each person going to get? Essentially nothing. And so as this increases to infinity, that 1 divided by x is going to basically turn into nothing or approach 0. Well, that wasn't so bad, just picking those values and seeing what happened. But what would happen if we wanted to evaluate the limit as x approached infinity of this function here? Can you imagine trying to make this same table, plugging in 1, 10, 100, 1,000, a million, all the way up into this function right here? It would take a really long time, and you would see it would become very, very tedious. So there is a shortcut. When you are taking the limit of a rational function, which is a polynomial divided by a polynomial, as x is approaching either positive or negative infinity, what you can do is actually just create a new fraction and reduce. And that new fraction will be the largest term, variable term in the numerator over the largest term in the denominator. And then you will reduce. And when you do this, one of three things is going to happen. Either the variable itself will completely cancel, and you're just left with a number. And if that's the case, then that's your limit. What may happen is that once you've canceled everything, you're left with a variable in the denominator. If that's the case, then your limit is 0. And then the other case is that once you reduce everything, you're left with a variable in the numerator, and then that means that your limit's either going to shoot up to positive or shoot down to negative infinity, and you will need to determine which one. Now, one special thing to note is that if your limit as x is approaching positive or negative infinity approaches a real defined value, we'll call it b, that means that the horizontal line y equals b forms a horizontal asymptote, which is that imaginary horizontal line that your function is going to get really close to, but never cross. Let's look at some examples. So let's revisit that example I had up before. Let's take the limit as x approaches infinity of this rational function right here. So according to our little shortcut, we're going to take the highest power of the variable up top over the highest variable power in the bottom. And we can see that's 4x to the 5th over negative 2x to the 5th. Once we reduce, these x to the 5ths cancel, and 4 divided by negative 2 is negative 2. So this is the same. These three limits are the same. So the limit as x approaches infinity of negative 2, as x increases positive without bound, negative 2 will stay as negative 2. Like we said, if you get a number in the end, then that is your limit. So what does this mean graphically? The line y equals negative 2 is a horizontal asymptote of this rational function right here. Let's do another one. Let's look at the limit as x approaches negative infinity of this big rational function here. So again, what we're going to do is we're going to take the biggest variable term in the top, which will be x cubed, so negative 4x cubed, and the biggest x value in the bottom, which will be negative x cubed here, and we'll just make a new fraction, biggest term over biggest term, and reduce. The x cubes cancel, and negative 4 over negative 1 becomes a 4. And so as x increases negative without bound, 4 remains as 4. And that does mean that y equals 4 is a horizontal asymptote of this rational function here. Let's look at another one. The limit as x approaches infinity of this rational function here. Again, what we're going to do is take the biggest term of x in the top, the biggest power of x in the bottom, and reduce them. And when we reduce that, we end up with 7 over x. That was one of the cases we talked about. If you're left with a variable in the denominator, then your limit is going to be 0. And so that's still a real defined value. So because that limit as x approached infinity gave us a real defined value, that means that y equals 0 is a horizontal asymptote of this rational function here. Let's look at the limit as t approaches negative infinity of this function right here. The variable itself doesn't matter. I know we've been working with x's, but it can be t. So we'll take the highest power of t term from the top, the highest power of the t term in the bottom, and make our new limit. The limit as t approaches negative infinity will reduce this. The t to the fifth and the t to the eighth will reduce to a t to the third in the bottom. Again, we're left with a variable in the denominator, so that means that our limit is going to be 0. This will also mean that y equals 0 is a horizontal asymptote of this rational function of t right here. Let's look at the limit as x approaches infinity of this right here. All right, so we'll take the biggest power of x over the biggest power of x and reduce. Now here we're left with the limit as x approaches infinity of 4x over 3. We have a variable in the numerator. This was the third case we talked about, and we said when this happens, when you're left with a variable in the numerator, then your limit's going to go off to one of the infinities, and you will need to determine which one. Well, let's see what happens. X is increasing positive without bound, which means x is a really big positive number. So x is positive. Take a positive number times 4, you're going to get another positive number. Take a big positive number and divide it by 3, and you're still going to get a positive number. So this will go off to positive infinity. Now, infinity isn't a real defined value. It's just a representation that numbers increase positive forever and they increase negative forever. So we don't get a horizontal asymptote here. Let's look at another one. The limit as x approaches negative infinity. Again, we'll take the biggest term of x over the biggest term of x. And when we do that, we get 6x cubed over 2x, negative 2x, and we reduce. And we're left with the limit as x approaches negative infinity of negative 3x squared. Now the fraction went away when it reduced, but that's still over 1, so we still have a variable left in the numerator. So this means that this limit is going to go off to either positive or negative infinity, and we will need to determine which one. Well, x is increasing negative without bound, which means x is a really big negative number. Take a really big negative number and square it, you get a positive number. Take a really big positive number times negative 3 and you're going to get a negative number. So this is going to go off to negative infinity. No horizontal asymptote here. Let's look at another example. The limit as a approaches infinity of this right here. So again, we'll take the biggest power of a over the biggest power of a and we will reduce. This gives us the limit as a approaches infinity of negative a cubed over 4a squared, which reduces to the limit as a approaches infinity of negative a over 4. Here we are left with a variable in the numerator, so this limit will shoot off to either positive or negative infinity, and we will need to determine which one. So a is increasing positive without bound. A is a really big positive number. Negative a makes it a really big negative number. Divided by 4, it's a negative number, so this is going to go off to negative infinity. So I want you to notice that just because a is approaching positive infinity doesn't mean that my limit approaches positive infinity. Sometimes these don't match. Couple more examples. Limit as x approaches negative infinity. Again, we'll take the biggest term of x over the biggest term of x and reduce. Here, x is increasing negative without bound. So you get 3 times a really big negative number cubed. A really big negative number raised to the third power will give you a negative. Times 3 stays negative. Divided by a negative becomes positive. So this one goes off to positive infinity. Again, just because the x is approaching negative infinity doesn't mean that the function approaches negative infinity. What I want you to do here is pause. And there are 3 more examples of limits at infinity that I want you to try on your own. And then I want you to hit play when you're done, and I will solve those for you in just a minute here, so you can see if you were able to do those last 3 examples correct on your own. The first one, the limit as m approaches infinity of 3m squared plus 2m minus 3 over 4m to the 5th plus 3m plus 2. Take the highest power of n over the highest power of n and reduce. Here we're left with a variable in the denominator that automatically means my limit goes to 0. What does that mean? That's a real defined value. That does mean that y equals 0 is a horizontal asymptote. Next one, this limit as x approaches infinity. We'll take the biggest power of x over the biggest power of x and reduce. Here we're left with a number, so as x increases positive without bound, 4 over negative 7 stays as negative 4 over 7. And so we do have a limit. It's -4/7. And that does mean that the horizontal line y equals -4/7 is a horizontal asymptote. Last one for limits at infinity. The limit as x approaches -infinity of this right here. We'll take the biggest power of x divided by the biggest power of x and reduce. We're left with an x in the numerator. That means this limit will go up to one of the infinities. X is increasing negative without bound, so it's a really big negative number. A negative number raised to an odd power is negative, times 3 is negative, divided by 7 is negative, so that goes off to -infinity. That's it for limits on infinity. We'll pick up next time with continuity. See you next time.